Gases in chemical reactions. Sometimes in a chemical reaction we have a reactant or a product that's in the gas state, or sometimes all of the reactants and products are in the gas state. In these situations, the amount of gas is usually specified in terms of volume at a specific temperature and pressure, because the mass of a gas is not a very useful thing. It's not all that easy to measure the mass of a gas. So when we have a situation like this, we're going to use the ideal gas law to convert the pressure, volume, and temperature to moles. So if we remember, the ideal gas law is PV inert, PV equals nRT. And we can rearrange that to solve for N. So the number of moles of a gas is equal to the pressure times the volume divided by the ideal gas constant and the temperature. And so this is how we can include gases in stoichiometry calculations. And the rest of it continues in the same pattern. So what did we chant for stoichiometry? Grams to moles to moles to grams, right? Grams to moles to moles to grams. I don't know what happened to my arrows. So this part, the moles to moles, is always the same. Stoichiometry always involves a mole-to-mole calculation. The ends can be different. Instead of a mass of a reactant, we could have a volume of a gas at a particular temperature and pressure. In that situation, we use the ideal gas law to take this information and convert it into moles. And then we continue on and we can find mass of product. Or volume of a gas could end up as one of the products. So let's look at this reaction. 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver 1 oxide decomposed? So here's our balanced chemical equation. The balanced chemical equation is really the center part of the stoichiometry. And so let's take these numbers and write them under the appropriate things here. So this is volume of oxygen. So 4.58 liters of oxygen. And then it gives me the pressure, 745 millimeters of mercury. And it gives me the temperature, 308 Kelvin. And then it's asking for how many grams of this. So our path is going to be from the component that we are given information about to moles to this that's asked for, the grams. So it's going to be volume to moles to moles to grams. Well, how do we take a volume of a gas and find the number of moles? Ideal gas law, right? So the number of moles of gas equals the pressure times the volume over RT. We have to be careful of units, though. Is liter an okay unit for the volume? Yeah. Is millimeters of mercury okay for the pressure? No. It needs to be in atmospheres. So we need to convert that to atmospheres. We would do that by dividing by 760. So converting this to atmospheres, we get 0.980, and I'm going to throw in 2 extra digits, and that's atmospheres. Is Kelvin a good unit for temperature? Yes, it is. So now we can plug these numbers into our equation over here. The pressure is 0.98026 atmospheres. The volume was 4.58 liters. And all of that's divided by R, which is always the same, 0.0821 liter atmospheres per mole Kelvin, times the temperature, 308 Kelvin. So N equals the 0.98026 times 4.58 divided by 0.0821 divided by 308. And the calculator says 0.177. This should have 3 significant figures also. I'm going to throw in 2 extras to avoid rounding errors by 5. And the unit on that is moles. That's moles of oxygen. So we use the ideal gas law to get from volume to moles of oxygen. Now we just finish it in the normal way. So we got this 0.01, that's not a 1, 17755 moles of oxygen. I want to convert that to what? Moles of something. I'm here, I'm trying to go to here. We're at moles, we need to go to moles and then to grams. So I'm going to convert it to moles of what I'm trying to find. And then what's next? Grams of that. You guys with me? So normally we go grams to moles to moles to grams. Right? This time though, they didn't give us a mass, they gave us a volume and temperature and pressure for a gas. We used the ideal gas law to find the moles. Now we can go back to our pattern. We're going to do moles to grams. So here's moles to grams. Then we put the previous unit in for the denominator because we want those units to cancel out. And then down here I'm going to get moles of Ag2O. We'll cancel that one. Where do we get the numbers for the mole to mole ratio? From the equation. The balanced chemical equation tells us 2 moles of this give us 1 mole of that. So I got a 2 here and a 1 there. And then how do we figure out the number for that last part? Periodic table. I think it's 107? 107.9. So silver is 107.9 times 2 plus the mass of oxygen, which is 16. That's 231.8. 231.8. So 0.017755 times 2 times 231.8, and that gives me 8.23 grams of silver oxide. I rounded that to 3 significant figures because this one had 3 sigfigs. Any questions? Yes?
Isn't it 0.1775?
Yes, it is. Thank you. Yeah, thank you very much. Yeah, so it would be 82.3, because I don't know where I got that from. Thank you. Any other questions?
How did you get R 0.0821?
R is always 0.0821. It's a constant.
Okay.
And the units are liter atmospheres per mole Kelvin, which tell us the units that we need to use for pressure, volume, and temperature, so that the units cancel out. Any other questions? N stands for number of moles of a gas. Anybody else? Questions are good. Standard temperature and pressure is abbreviated STP for standard temperature, pressure. And it's one atmosphere and 0 degrees Celsius, which is equal to 273 Kelvin. This was chosen as a standard reference temperature and pressure for gases, I think because it's easy to obtain. Remember, many of these gas experiments and laws were determined long before electricity was discovered, right? They didn't have refrigerators or electronic temperature controlled devices back then. So how do you control the temperature of your gas? Well, it's either going to be whatever temperature it wants, or you could put the container in a big ice bath and know that it's at 0. And so that was convenient. And then just like we did in lab, where we adjusted the level of the liquids inside and outside the container so that the pressure was the same as outside, the external pressure is generally about 1 atmosphere. And so that's also an easy pressure to obtain experimentally. So thinking of it that way helps me to remember what standard temperature and pressure are. It's the freezing point of water in ice bath temperature and regular atmospheric pressure. So let's calculate the volume of 1 mole of a gas at STP. Well, how do we calculate the volume of a gas? PV equals nRT. So we're going to rearrange this and solve it for V. So I'm going to do that. Volume of 1 mole. So what's N? 1. 1 mole of gas. What's R? 0.0821 liter atmospheres per mole Kelvin. What's the temperature? 273. At STP, which always makes me think of motor oil, at STP, the temperature is 273. Anytime you see STP, that is telling you the temperature and the pressure. So this is 273 Kelvin. And then we're dividing by the pressure. The pressure is 1 atmosphere. So when we do this calculation, we come up with 22.4 liters. Do it on your calculator and prove it to yourself. This is the volume of 1 mole of gas. What kind of gas? It doesn't matter. Any gas. I know, it's weird, huh? The volume of any gas, 1 mole of it at STP, is 22.4 liters. So we call this the molar volume of an ideal gas at STP. The molar mass was the mass of 1 mole. The molar volume is the volume of 1 mole. And we specify at STP. And so for any gas, the molar volume at STP is 22.4 liters per mole. This makes a very convenient conversion factor. If the gas is at STP, we don't have to use the ideal gas law to calculate the volume and the mole relativity. We can just use this number. So let's do an example. Or maybe let's just look at a picture instead. I don't know what's coming next. 2 pictures here. This is representing 1 mole of helium at STP. This is 1 mole of xenon at STP. Which type of atom is larger, helium or xenon? Xenon is. You know, as we go down a column in the periodic table, the size of the atom increases. Xenon's at the bottom, helium's at the top. Does the size of the particle matter in a gas? Nope. So the volume of this gas is 22.4 liters. The volume of the xenon is 22.4 liters. Are the masses the same? No. The masses are different, but the volumes are the same. It's weird. If we're doing stoichiometry with a gas at STP, it's easier. So here, how many liters of oxygen at STP are required to form 10.5 grams of water? So we're given 10.5 grams of water, and the question is, how many liters at STP? So our path here is grams of water to moles of water to moles of oxygen to a volume of oxygen. Liters. 10.5 grams of water times moles, water. Sorry for my defective twos today. My stylus is not happy with me for some reason. There we go. To moles of oxygen to liters of oxygen. Previous unit goes in the bottom. This is just that pattern we learned for dimensional analysis. This would be grams of H2O. Grams per mole, this is the molar mass of oxygen, 2 times the mass of hydrogen plus the mass of oxygen, it's 18.02. What's the mole ratio of oxygen to oxygen to water in this equation? 1 to 2. 1 mole of oxygen to 2 moles of water. There's a 2 here and a 1 there. And then what's the relationship between liters of oxygen and moles of oxygen at STP? 22.4. Isn't that cool? So 22.4. That works for any gas at STP. Isn't that easier than pulling out the ideal gas law and calculating? Yeah, it is. 10.5 divided by 18.02 divided by 2 times 22.4. This result should have 3 sig figs, so 6.53 liters. Did I get it right that time? Okay. Any questions? If you were given a volume of gas at STP and asked for a mass, you could use the 22.4 as your first conversion factor. And that's the end of the chapter. Thank goodness.